Astronomers have just calculated the precise size of interstellar object 3I/Atlas, and the number they arrived at changes everything we thought we knew about our cosmic neighborhood. After months of intensive observations using the Hubble Space Telescope, tracking this mysterious visitor from another star system as it careened through our solar system, scientists can now confirm that 3I/Atlas measures 1.3 kilometers in radius. That gives it a diameter of 2.6 kilometers, making it roughly the size of a small mountain and significantly larger than the previous interstellar objects we've detected. But here's where things get interesting. This isn't just about measuring one cosmic iceberg. This single measurement has allowed researchers to calculate something far more profound: the probability of interstellar objects passing through our solar system at any given moment. And those calculations reveal a startling truth. Based on the size of 3I/Atlas, the dimensions of the two previous interstellar visitors, and the frequency of their detection, scientists now estimate that approximately one interstellar object passes within Jupiter's orbit every single year. Every year. We've been operating telescopes and sky surveys for decades, yet we've only confirmed 3 interstellar objects. That mathematical discrepancy tells us something crucial. We're not alone out here. We're surrounded. Our solar system is being visited constantly by cosmic travelers from distant star systems, and until very recently, we were completely blind to them. In this video, we will explain how scientists measured 3I/Atlas with unprecedented precision, why this particular measurement matters so much, what it reveals about the unseen population of interstellar objects streaming through our cosmic backyard, and what this means for the future of astronomy, planetary defense, and our understanding of how star systems interact across the galaxy. Let's get started. The story of interstellar objects is remarkably recent. For most of human history, we assumed our solar system was a closed environment, a gravitationally bound family of planets, moons, asteroids, and comets that all originated from the same primordial disk of gas and dust 4.6 billion years ago. Everything we observed orbited the sun in predictable elliptical paths. Comets would swing in from the distant Oort cloud, loop around the sun, and head back out on their long elliptical journeys. Nothing came from outside, nothing left permanently. That assumption shattered on October 19, 2017, when astronomer Robert Warwick, using the Pan-STARRS telescope in Hawaii, spotted an object with a trajectory that didn't make sense. The object, later designated 1I Oumuamua, was moving too fast. Its orbital path was hyperbolic, not elliptical. That meant it wasn't bound to our sun's gravity, it was just passing through. For the first time in recorded history, humanity had detected a visitor from another star system. Oumuamua presented more questions than answers. It was small, moving incredibly fast, tumbling end over end, and by the time we realized what we were looking at, it was already racing away from the sun. We barely got a handful of observations before it vanished into the darkness of interstellar space. Scientists scrambled to analyze the limited data. The object was elongated, possibly cigar-shaped, measuring roughly 400 meters in length. It showed no signs of outgassing, the telltale jets of vapor that comets produce when they're heated by the sun. Its acceleration was slightly anomalous, leading to intense debate about whether it was affected by radiation pressure, outgassing we couldn't detect, or something else entirely. We had discovered interstellar objects existed, but we had almost no information about what they actually were. 2 years later, in August 2019, amateur astronomer Gennady Borisov, observing from his backyard observatory in Crimea, spotted another anomaly. This object, designated 2I/Borisov, was also on a hyperbolic trajectory, also moving too fast to be gravitationally bound to the sun. But 2I/Borisov was different from Oumuamua in crucial ways. This one behaved like a comet. It had a tail, it was outgassing, it glowed in a way that suggested it contained familiar materials: water, ice, carbon monoxide, the building blocks we see in comets from our own solar system. And crucially, we detected it earlier in its approach, giving astronomers months to study it with multiple telescopes before it swung around the sun and disappeared forever. These 2 detections established a pattern. Interstellar objects weren't theoretical anymore. They were real, they were detectable, and apparently, they weren't that rare. But we still had fundamental questions. How common were these objects? What sizes did they come in? Were we seeing a representative sample? Or were we only catching the largest, brightest ones? while thousands of smaller visitors slipped past unnoticed. And most importantly, what did their existence tell us about the galaxy we inhabit? That's where 3I/Atlas enters the story. Discovered in 2025, this third confirmed interstellar visitor arrived at a time when our detection capabilities had significantly improved. We had more sky surveys running, we had better algorithms for identifying unusual trajectories, we had the institutional knowledge from studying the first two interstellar objects, so we knew what to look for. When 3I/Atlas appeared, astronomers were ready. The breakthrough measurement of 3I/Atlas didn't happen overnight. It required months of painstaking observation, careful analysis, and sophisticated modeling. Between November 2025 and January 2026, the Hubble Space Telescope conducted an intensive observing campaign, tracking 3I/Atlas as it traveled through the inner solar system. This wasn't a simple point-and-shoot operation. 3I/Atlas was moving at tremendous velocity, the fastest object ever observed passing through our solar system. Keeping it centered in Hubble's field of view required precise coordination and rapid adjustments. The team collected multiple images across different dates, creating what astronomers call a light curve, a record of how the object's brightness changed over time. But there was a complication. During the observation period, Hubble experienced a solar panel malfunction that created a gap in the data collection between January 15th and January 18th. The engineering team worked to restore functionality, and once the telescope was operational again, they resumed imaging. The scientists then stacked all the captured images together, creating a composite that revealed 3I/Atlas moving against the background stars. In these processed images, the background appears to shift because the software keeps 3I/Atlas fixed in frame, compensating for its motion. What they observed was revealing. The object showed evidence of activity, releasing particles into space, but in an unexpected way. Early processing suggested a sunward-facing tail, the classic comet signature where solar radiation pressure pushes material away from the sun. But more detailed analysis revealed something different. The material streaming off 3I/Atlas was actually pointing in the anti-velocity direction. In other words, if 3I/Atlas was moving forward through space, particles were being pushed backward, opposite to its direction of travel. This suggests a combination of processes at work: dust and grains being shed from the surface, plasma interactions with the solar wind, electromagnetic forces acting on charged particles. It's a reminder that space environments are complex, and simple Earth-based intuitions about how things should behave don't always apply. But the most important result from this observing campaign was the size calculation. To determine the physical dimensions of a distant object, you need two pieces of information: how bright it appears and how reflective its surface is. Brightness alone doesn't tell you much. A small, highly reflective object can appear just as bright as a large, dark object. You need to know the albedo, the percentage of sunlight the object reflects. For 3I/Atlas, astronomers assumed an albedo of 0.04, meaning the object reflects only 4% of the light that hits it. This is consistent with what we observe in comets from our own solar system, particularly long-period comets from the Oort cloud, which tend to have dark, carbon-rich surfaces covered in organic compounds. Using this albedo value and the measured brightness, the team calculated the radius at 1.3 kilometers, with an uncertainty margin of plus or minus 0.2 kilometers. That translates to a diameter of approximately 2.6 kilometers, or just under 2 miles across. This makes 3I/Atlas significantly larger than both previous interstellar objects. Oumuamua measured roughly 400 meters at its longest dimension. 2I/Borisov was estimated at around 500 to 600 meters in diameter. 3I/Atlas is 4 to 5 times larger than either of them. Early, more speculative estimates had suggested it might be as large as 50 kilometers across, which would have been extraordinary, potentially the largest comet-like object ever observed. The confirmed size of 2.6 kilometers places it firmly in the normal range for cometary bodies, but on the larger end of that range. To put this in perspective, 2.6 kilometers is roughly the size of Mount Vesuvius, the volcano that destroyed Pompeii. It's about half the length of Manhattan Island. If an object this size were to impact Earth, it would be an extinction-level event, releasing energy equivalent to millions of nuclear weapons. This isn't a pebble, it's a planetesimal, a building block left over from planetary formation in whatever star system it came from, now wandering the galaxy on a trajectory that just happened to intersect with our solar system. As of early February 2026, 3I/Atlas is located between the orbits of Mars and Jupiter, currently at a distance of approximately 5.2 astronomical units from the Sun. 1 astronomical unit, or AU, is the distance from the Earth to the Sun, roughly 150 million kilometers. Mars orbits at about 1.5 AU, Jupiter sits at 5.2 AU. 3I/Atlas entered our solar system from beyond Neptune's orbit back in 2016, past its closest point to the Sun, called perihelion, in late 2025, and is now heading outward. Its closest approach to Jupiter will occur on March 17, 2026, after which it will continue accelerating away, eventually leaving our solar system entirely, never to return. The object's trajectory is what astronomers call hyperbolic. Unlike the elliptical orbits of planets and comets native to our solar system, which loop back around the Sun in predictable cycles, a hyperbolic trajectory is a one-way trip. The object came from interstellar space, curved around the Sun due to gravitational influence, but had more than enough velocity to escape. The Sun's gravity will tug on it, bend its path, slow it down slightly, but it won't capture it. 3I/Atlas will leave our solar system and continue wandering the galaxy until it encounters another star system, potentially millions of years from now. This is where the story shifts from describing one object to understanding an entire population. The size measurement of 3I/Atlas isn't just a data point. It's a key that unlocks a much larger question. How many interstellar objects are actually out there? Scientists approach this problem statistically. They had 3 confirmed interstellar objects: Oumuamua in 2017, 2I/Borisov in 2019, and 3I/Atlas in 2025. They had size estimates for all 3. They had trajectory data showing where these objects traveled through our solar system, and they had information about the detection capabilities of our sky surveys, which telescopes were operating when, what regions of sky were being monitored, and what the detection thresholds were for objects of different sizes and brightnesses. Using this information, researchers constructed a model. If we detected 3 interstellar objects over a span of roughly 8 years, and if those objects had the sizes we measured, how many total interstellar objects must be passing through our solar system to produce that detection rate? The calculation has to account for observational bias. Larger objects are easier to detect, brighter objects are easier to detect. Objects that pass close to Earth are easier to detect than objects that stay in the outer solar system. Objects that arrive when multiple sky surveys are operating are more likely to be found than objects that arrived decades ago when we had fewer telescopes and less sophisticated detection algorithms. The results were striking. According to a recent research paper analyzing this question, there should be approximately 1 interstellar object passing within 4.5 astronomical units of the Sun every single year. That distance, 4.5 AU, is just inside Jupiter's orbit. It represents the inner and middle region of our solar system, the zone where we have the best chance of detection because objects there are relatively close, relatively well illuminated by the Sun, and located in regions of sky that surveys monitor regularly. 1 per year, we've detected 3 in 8 years. That means we're missing approximately 80% of the interstellar objects that pass through this region. They're there, they're real, they're moving through the space between Mars and Jupiter, and we're not seeing them. Why not? Several reasons. First, many of these objects are probably small and dark. If an object is only a few hundred meters across and has a low albedo, it will be extremely faint, even when relatively close to the Sun. Our telescopes can detect it in principle, but only if we're looking at exactly the right patch of sky at exactly the right time. Second, interstellar objects move fast. They're not gravitationally bound to the Sun, so they're moving at velocities of 20, 30, sometimes 40 kilometers per second or more. That means they pass through the inner solar system in a matter of months, sometimes weeks. If a survey happens to be pointed at a different part of the sky when the object is at its brightest, we'll miss it. Third, these objects don't always behave predictably. Some show comet-like activity, developing tails and comas that make them easier to spot. Others, like Oumuamua, are inert, just dark chunks of rock or ice that reflect almost no light. Now expand the analysis beyond 4.5 AU. If we're talking about the region out to Neptune's orbit, at 30 AU, the volume of space increases dramatically. We're no longer talking about a relatively narrow disk around the Sun. We're talking about a vast spherical volume that extends above and below the plane of the solar system. Interstellar objects don't have to follow the ecliptic, the flat plane where planets orbit. They can come from any direction, from above, from below, from the sides, and our detection capabilities in those regions are far more limited. In that larger volume, the number of interstellar objects present at any given time could be dozens, possibly hundreds. They're out there, drifting through the Kuiper belt, moving through the space between Uranus and Neptune, passing above or below the plane of the solar system, where very few surveys ever look. Most of them will never be detected. They'll pass through our cosmic backyard completely unnoticed, invisible travelers on journeys that began light years away. This realization fundamentally changes our understanding of the solar system. We used to think of it as an isolated island, a closed system shaped entirely by the sun's influence and the primordial material that formed here 4.6 billion years ago. Now we know that's not true. Our solar system is porous. It's constantly being visited by material from other star systems. We exist in a dynamic galactic environment where matter flows between stars, where planetary systems exchange material over millions and billions of years, where the building blocks of worlds wander the galaxy until gravity pulls them into new orbits around new suns. The implications go deeper. If interstellar objects are this common now, they must have been common throughout Earth's history. These visitors have been arriving for billions of years, long before humans existed, long before any life existed. Some of them may have impacted Earth or other planets. Some may have delivered organic compounds, water, or other materials that contributed to the chemical evolution that led to life. We've always known that asteroids and comets from within our solar system bombarded the early Earth. Now we have to consider that some of those impacts may have come from interstellar space, carrying chemistry from entirely different star systems, potentially seeding Earth with the building blocks of biology that originated light years away. The confirmation that interstellar objects are common visitors has practical consequences that extend far beyond academic interest. One of the most immediate is planetary defense. NASA and other space agencies maintain programs dedicated to detecting and tracking near-Earth objects, asteroids, and comets that could potentially impact our planet. The goal is to catalog as many of these objects as possible, calculate their orbits, and identify any that pose a collision risk years or decades in advance. Interstellar objects complicate this mission. They don't follow predictable orbits. They arrive from random directions at high velocities with essentially no warning. Oumuamua was detected as it was already leaving the inner solar system. If an object like 3I/Atlas were on a collision course with Earth instead of passing harmlessly through the asteroid belt, we would have very little time to respond. The object could be detected months before impact, possibly only weeks, far too little time to mount any kind of deflection mission with current technology. This doesn't mean interstellar object impacts are likely. Space is vast, Earth is small. The probability of a specific interstellar object hitting our planet is extremely low, but extremely low is not the same as zero, and when the potential consequence is a civilization-ending impact, even low probability events demand attention. Knowing that roughly one interstellar object per year passes within Jupiter's orbit means we need detection systems that can spot these visitors as early as possible, ideally when they're still beyond Neptune, giving us maximum warning time. This is where next-generation sky surveys become critical. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, or LSST, beginning operations in the mid-2020s. This observatory will photograph the entire visible sky every few nights, creating a constantly updating map of everything that moves or changes. It will detect asteroids, comets, supernovae, variable stars, and yes, interstellar objects. With LSST online, our ability to find these cosmic visitors will increase by orders of magnitude. We'll start detecting interstellar objects when they're still in the outer solar system, giving us months or years to study them instead of weeks. We'll be able to measure their sizes, compositions, rotation rates, and activity levels. We'll build a statistical census of what types of objects are out there, what materials they're made of, how their properties vary, and critically, we'll spot any that might pose a threat far enough in advance to matter. Beyond planetary defense, the scientific value of detecting more interstellar objects is immense. Each one is a sample of another star system delivered directly to our doorstep. We don't have to send spacecraft across light years of distance to study exoplanetary systems. The galaxy is sending us samples naturally. By analyzing the composition of interstellar objects, we can learn what kinds of materials exist around other stars, whether they're similar to what we have in our solar system or fundamentally different. For example, 2I/Borisov showed evidence of carbon monoxide in its outgassing at concentrations higher than typical comets from our solar system. That tells us something about the chemistry of the system it came from, possibly indicating a different formation temperature or different abundances of volatile elements. 3I/Atlas, with its larger size and evidence of activity, offers another data point. As we detect more objects, we'll start to see patterns. Are most interstellar objects icy and comet-like, or are rocky asteroids common too? Do they cluster in certain size ranges, or is there a continuous distribution from small pebbles to massive planetesimals? What does the population distribution tell us about planetary formation processes in other star systems? There's also the tantalizing possibility of sending a spacecraft to intercept an interstellar object. This was seriously proposed for both Oumuamua and 2I/Borisov, though neither mission moved forward due to the extreme velocity requirements and short timescales. But with better advanced detection, a rapid response mission becomes more feasible. Imagine a spacecraft designed to launch on short notice, intercept an interstellar visitor while it's still in the outer solar system, match its velocity, and ride alongside it for months, conducting detailed observations and even returning samples to Earth. This would be the ultimate form of interstellar exploration, studying another star system's material without leaving our own cosmic neighborhood. The technology for such a mission is within reach. We have the rockets, the propulsion systems, the instruments. What we need is early detection and sufficient warning time. With LSST and future surveys, that becomes possible. We could have our first interstellar object rendezvous mission launched within the next decade, depending on when the next suitable target appears. Looking further ahead, the study of interstellar objects connects to one of the most profound questions in science: how common are planetary systems like ours, and what does the architecture of other systems tell us about the formation of our own? Every star system forms from a disk of gas and dust. Planets coalesce from that material, sweeping up most of the available mass, but not all of it. Leftover planetesimals, the building blocks that never got incorporated into planets, remain scattered throughout the system. Some are gravitationally ejected by interactions with giant planets, flung into interstellar space at high velocities. Our solar system did this. Jupiter and Saturn, during their early migration and gravitational interactions, scattered countless objects. Some fell into the sun, some were ejected entirely, sent on one-way trips into the galaxy. That means our solar system has contributed to the interstellar object population. Somewhere out there, fragments of our Kuiper belt are wandering between the stars, just as fragments from other systems visit us. By studying the interstellar objects that arrive here, we're essentially sampling the debris fields of distant planetary systems. We're seeing what gets left over after planets form. We're learning about the ejection processes that shape planetary system architecture, and we're gathering clues about how common different types of planetary systems are across the galaxy. For instance, the size distribution of interstellar objects can tell us about the efficiency of planet formation in other systems. If we detect mostly large objects like 3I/Atlas and very few small ones, that suggests certain formation processes dominate. If we find a wide range of sizes, that tells a different story. The composition ratios, how many icy objects versus rocky objects, can indicate what the original protoplanetary disks were made of, which in turn depends on the metallicity of the parent stars and the conditions in the molecular clouds where those stars formed. This is galaxy-scale archaeology. We're using the debris from ancient planetary formation events to reconstruct the history of star systems across our local region of the Milky Way. And it all starts with measurements like the one just completed for 3I/Atlas. One size estimate, combined with detection statistics, opens a window into understanding billions of years of galactic evolution. There's also a human element to this story that shouldn't be overlooked. For thousands of years, Humans have looked at the sky and wondered what else is out there. Are we alone? Are there other worlds? What exists beyond the familiar planets and stars? For most of history, we could only speculate. Now we're living in the era when we're finding the answers, not through radio signals from alien civilizations, but through direct physical evidence. Rocks from other star systems, ice from alien oceans, material that formed around stars we can't even identify, now drifting through our cosmic neighborhood, carrying information encoded in their chemistry and structure. We didn't have to build starships to find this material. It came to us, the galaxy delivered samples to our doorstep, and we finally have the technology to notice them. That's remarkable. It means the barrier between us and the rest of the galaxy is lower than we imagined. We're not isolated, we're connected. Matter flows between star systems, chemistry is exchanged. The galaxy is a more dynamic, interactive place than the static model we once held. And we're only at the beginning of this discovery process. 3 confirmed interstellar objects. Statistical models suggesting dozens more pass through unnoticed every decade. Observatories coming online that will increase detection rates by factors of 10 or more. Within a generation, we'll likely have detected hundreds of interstellar visitors. We'll have data on their sizes, compositions, velocities, and origins. We'll start to see them not as rare anomalies, but as a routine part of the solar system environment, cosmic commuters passing through on their billion-year journeys across the galaxy. Right now, in February 2026, 3I/Atlas is moving through the space between Mars and Jupiter, approaching its closest encounter with the solar system's largest planet. Within weeks, it will swing past Jupiter at a distance that, while safe, represents the nearest approach a confirmed interstellar object has made to one of our gas giants. Astronomers will continue tracking it, gathering data on how Jupiter's gravity affects its trajectory, measuring any outgassing or activity as it moves through different regions of the solar system. Within a few months, 3I/Atlas will cross Jupiter's orbit and continue outward, passing through the asteroid belt, moving toward the realm of the outer planets. Within a year, it will be beyond Saturn. Within a decade, it will pass the orbit of Neptune, entering the Kuiper Belt region where it first entered our detection range back in 2016. And then, within a few more decades, it will leave entirely, fading into the darkness of interstellar space, traveling onward to whatever destination the galaxy has in store. But 3I/Atlas is not the end of this story. It's a chapter in a much longer narrative that spans billions of years and light years of space. Somewhere out there, right now, other interstellar objects are approaching our solar system. They're invisible to us, too far away, too dark, moving through regions of space we don't monitor. But they're coming, and with each passing year, our ability to detect them improves. Our sky surveys get better, our algorithms get smarter, our understanding deepens. Within the next few years, we'll detect interstellar object number 4, then 5, then 10. Each one will add to our knowledge. Each one will be a messenger from a different star system, carrying information about worlds we cannot visit, chemistry we have never sampled, history we are only beginning to understand. And with each detection, the realization will become more concrete. We are not isolated. Our solar system is part of a galaxy-wide network of matter exchange, a cosmic ecosystem where material flows between stars, where the building blocks of worlds wander for millions of years before finding new homes. This is the true significance of measuring 3I/Atlas. It's not just about one object, it's about revealing a hidden population that has surrounded us all along. It's about understanding that the galaxy is more interconnected than we imagined. It's about recognizing that Earth, our solar system, our sun, exist within a dynamic environment shaped by forces and processes that span the entire Milky Way. And it's happening now. The discoveries are being made today. The data is being collected this year. The papers are being published this decade. We are living through the era when humanity transitions from believing we're alone in a static solar system to knowing we're part of a galactic community of matter and energy, constantly exchanging material, constantly interacting, constantly evolving. The size of 3I/Atlas is 2.6 kilometers. But the implications of that measurement stretch across light years and billions of years, connecting us to star systems we've never seen, to planetary formation events that occurred before our sun existed, to a future where interstellar objects are as familiar to us as comets and asteroids, regular visitors from the wider galaxy that we study, track, and eventually perhaps explore. If you want to support our work in bringing you these deep dives into the latest astronomical discoveries, consider joining our membership program. We're working to reach 1,000 members who believe in accessible, accurate science communication. Your membership directly supports the research, scripting, and production that goes into every video, allowing us to cover stories like 3i/Atlas in the depth they deserve. Join us in making science accessible to everyone and help us reach that 1,000 member milestone.